Okay, so that equation then simplified as this. Okay, it's a very nice simple equation. There's nothing much left. And so we are going to write final minus initials for deltas. Since we are doing from 2 to 3, 2 is initial, 3 is final, so it's nice to show it in terms of those labeling, because you have also 0.1, so there some initials will be final later. So instead of confusing yourself, just label it this way when you have multiple points. So hopefully this is clear, and then you are going to do one more simplification and think about if you have any zero values. For point 2 and 3 we have velocity, although we don't know what they are right now. We will think about that later. Gravitational potential, we need to look into the elevation. We said at point 2 y is 0, so if you go down, you can say I went two down. Okay, you can say that the at point 2 this is 0 as well, because y2 is 0. Okay, that's where we set our zero potential, and we show it here. So I cancel those out as well, and then I have 3 terms, and I'm writing those 3 terms. First one is 1/2 mv3 cube, and minus 1/2 mv2 square, not cube, and plus mgy3. Okay, that's equal to 0. Now let's kind of think about this. So first thing I see is mass is going to go away. So even if I don't have it, I don't really need it for this equation. It's not going to matter. So don't panic because the mass is not given. Sometimes this is what's going to happen, okay? It will just disappear. And I usually also get rid of 1/2 so I can multiply everything by 2 to clarify a little bit. So I could just write this as multiplying 2 each term. This becomes v3 squared minus v2 squared plus 2gy3 equals to 0. I got rid of the masses as well, right? It's a nice equation. The problem is I'm not given any of the velocities, right? But I know what 2gy3 is. y3 is 8.5 feet. So it looks like there are 2 unknowns, though. What do we do? At this point, I want you to kind of think about it first. You can pause it and think about it and then come back. We are going to make use of projectile motion, okay? What we know about projectile motion. First of all, remember that I'm going to clear up some stuff here. Okay, remember that this was 8.5 feet is the maximum height, okay? So this is maximum. At point 2, this is your velocity, this is v2, and it has components, but at v3, this is your v3, okay? So if you look at the components, this is v2x, v2y, and I'm saying, again, for this case, I'm taking x and y this way, and v3 is only v3x, and v3y is simply 0, because this is the maximum. Remember that at the apex, it only has the x component. And if you remember, in projectile motion, x component does not change. That means this 2, v2x and v3x are the same. Okay, that's really important. So that's how we're going to relate them. So although they look like two different two unknowns, there's a relation between them. Okay, so if you split, so in here, if we go back to our solution, if you focus on point 2 and look at the vectors, so this is what you see, right? This is nicely drawn, x and y components for v2, and then you can get what v2x is in terms of v2. And if you use the trigonometric function cosine theta, so if you write cosine theta, it would be v2x divided by v2. Rearrange it for v2x, this is what you get. And you can also write down v2y this in the same form. But since x components are the key to relate those two points, velocities, I'm gonna kind of focus on that. But again, this is also, I'm gonna write it this way. This is how you write the y component of v2. Okay, and next we are going to think about point 3. Okay, and this is what happens at point 3. There's only x components, and that's v3x. Once again, because of the projectile motion at the apex, it only has x component, and that x component doesn't change because it is a constant velocity along the x direction. Y component changes only, right? And we have 0y for the point 3. So again, v3 can be also written in the same form, and so what we are doing here, instead of using 2 and 3, we are labeling the velocity something common. So it's a muzzle velocity, so we can maybe use Vm instead of V2, so that would make it, give it a relation between V2 and V3, okay? So here we got those equations, the components, and we have V3 as well. So when you go back to the conservation of energy, where you see V2 squared, you're replacing V2 with the Vm and V3 with Vm cosine 35 degrees, okay, as we got it from the solutions. So yeah, this is V3, this was V2, okay, and you're squaring them. So this is how you make them a common unknown. So we really got rid of one of the unknowns, right? Now we have only one unknown. I'm gonna get rid of this so it doesn't block my equation. So you can see that the only unknown is this Vm, and simply leave Vm alone and then put everything else on the other side. After doing some kind of factoring out, I would already get rid of those masses, and they're gone on the second line. Once you get this equation, all you need to do is like plug the numbers in and check your units. It becomes feet square over second square, and taking square root, it gives you feet per second, and it is 40.8 feet per second. Okay, so that's how you do the energy conservation. And once in a while, again, you have only one equation, you may have more than one unknown, so you're gonna make a new plan, revise your plan at that point.